Hi everyone, this is Dr. Saida Falafini from Cal Poly Pomona. In this video, we are going to talk about city-state probabilities in a Markov chain. So let's see what do we mean by this concept. If you go back to the cola example, when we were talking about the scenario when we had two groups of people, cola 1 drinker and cola 2 drinker, if you remember, the one-state transition probability matrix was as below. But we stated that in Markov chains or stochastic processes, we are usually interested in analyzing the behavior of the system in future. We are interested to predict what is going to be the state of the system or the situation of the system in future. So, and that's why we learned the n-step transition probability metrics and how we can use them. So we, for example, learned that P5 in this matrix is so this matrix P5 is going to help us to see what is the probability that we end up at any one of the states as cola 1 drinker or cola 2 drinker if we know where are we right now. So this the first row is for cola 1 drinker and second row is cola 2 drinker, and similarly the first column and the second column. Okay, if we look at the first probability matrix, this one, so each element is going to tell us that, for example, if right now I'm a cola 1 drinker, what is the probability that in the next purchase I'm a cola 1 drinker too. But the elements on the P5 are going to tell us that if right now I'm a cola 1 drinker, what is the probability that 5 purchases from now I'm a cola 1 drinker too. So let's see now how P10 is going to change. So that P10L is helping us to see what would be the behavior of the system 10 purchases from now. So P10 is going to tell us that if, for example, I'm a cola 1 drinker right now, what is the probability that I still drink cola 1 10 purchases from now. As you can see, the probabilities of these transitions change as we go from P to P5 to P10 and so forth. So let's look at how these values are going to change as I increase the power, meaning that I want to predict the behavior of the system in a longer run, more into the future. So let's look at how P20 will look like. So this matrix is going to tell us that if I'm a cola 1 drinker right now with a chance of 67%, 20 purchases from now I will be a cola 1 drinker. No matter what type of transitions has happened in between, that's the prediction that with 67% chance I'm a cola 1 drinker 20 purchases from now, and with 33% chance I'm a cola 2 drinker 20 purchases from now. And then if I look at, for example, P30, this is what I get. So at P30, we see that these values didn't change at all compared to P20. So again, if I'm a cola 1 drinker right now, after 30 purchases, there is 67% chance that I'm a cola 1 drinker, and there is 33% chance that I'm a cola 2 drinker. And if we continue these calculations, if we go to P40, P50, P60, all the way, for example, to P100, to P200, and so forth, we will see that these transitions probabilities are not going to change anymore. So basically, as we try to predict the behavior of the system in future, so as we try to calculate Pn, we try to calculate the behavior of the system as n goes to infinity, we see that these transitions probabilities are actually converging to some values. So there are two things that we can see right now. One is that, as I told you, as n goes to infinity, these transition probability matrices converge. So that's one. The other thing is that if you look at the P20 or P30, you will see that the numbers on the first row and second row are the same. What does that mean? It means that if you want to see what is the probability that 20 purchases or 30 purchases or 100 purchases from now you are a cola 1 drinker, it doesn't matter where you are going to start from. Actually, no matter if you're a cola 1 drinker right now or a cola 2 drinker right now, there is 67% chance that you are a cola 1 drinker 20 purchases from now, and there is 33 purchases chance that you are a cola 2 drinker 20 purchases from now, no matter if you're a cola 1 drinker or cola 2 drinker at this right now. And the same for a P30 or P40 or P100. This means that as we try to predict the behavior of the system in the future, in the long run, these transition probabilities basically converge to some values, no matter what is the state of the system right now, no matter where we are going to start from right now. So these probabilities are what we call as steady state probabilities, and there are notations for them. We call them as pi 1 and pi 2. So these are what we call as a steady state probabilities, and these probabilities basically show the behavior of the system in the long run when the system reaches an equilibrium. That doesn't mean that the transitions are not going to happen. Still, the system goes through the transitions, but given the probability of one-step transitions, this is how we will find the system. If we stop the system in the long run after hundreds, 200s, thousands of transitions, if we stop the system and look at the system, there is 67% chance that the person is a cola 1 drinker, and there is a 33% chance that any specific person is a cola 2 drinker. So those are basically the behavior of this stochastic system in the long run, in the equilibrium, in the steady state. So for any stochastic processes, our goal is to be able to calculate these steady state probabilities and basically be able to say how the system will perform in the long run. Now we want to learn how potentially we can calculate such steady state probabilities, because obviously when we get a one-step transition probability matrix, we don't want to start just raising it to the power of 20, 50, 100, 200 and see when gradually the system starts to converge to some values and then pick those as steady state transition probabilities. There are actually ways for us to mathematically calculate what are the values for the steady state transition probabilities. So the very first thing that I want you guys to pay attention to is that the steady state transition probabilities exist for ergodic Markov chains. So, and that's why we learned all those classifications of the states of the system to see what is the definition of an ergodic Markov chain. Because if we want to calculate the steady state probabilities for a Markov chain, we first have to make sure that's an ergodic Markov chain, and then we can go ahead and calculate those transition probabilities. And just to explain to you this notation, Pn shows the n-step transition probability matrix when n goes to the infinity, meaning that the behavior of the system in the long run. And as you can see, the probability of being in state 1 converges to the value of pi 1, no matter where we start from. If we start from state 1, from state 2, all the way to state S, no matter where we are going to start from, in the long run, the chance of being at the state 1 is pi 1. In the long run, the chance of being at the state 2 is pi 2, no matter where we start from. So these are basically, as I said, the steady state transition probabilities, and that's the ones we want to calculate. So let's see how we do this. So we said in the steady state, in the long run, in equilibrium, we want this to happen. So basically for large n, probability of going from state I to state j in n plus 1 transition basically equals to probability of going from state I to j in n transitions, meaning that at some point all these transition probabilities are going to converge to specific numbers. So it doesn't matter if it's n step, n plus 1 steps, or so forth. So for large n, these transition probabilities are basically the same, and we are going to call them as pi j. We can also calculate pij n plus 1 as this summation of going from state I to any intermediate state k in n step, and then going from state k to state j in 1 step, right? Where k can go from 1 to s. That's just a transition. That's just the includes all the possibilities of going from state I to state j in n plus 1 step. Given the fact that we also know this equality holds, we can write this equation as sigma pi k multiplied by p k j, where k goes from 1 to s. So if you want to calculate pi j, meaning the probability of system being in state j in the long run, we have to basically calculate this equation to get to that point. So if I calculate pi j for all the possible states, so I will be able to, I will have pi 1, pi 2, all the way to pi s. Okay, so the probability that the system in the long run is in state 1, the probability that the system in the long run is in state 2, and all the way to state s. So this is what we call as vector pi, and that's what we call as city-state probabilities. And our goal is to be able to calculate this vector pi, or the vector of city-state probabilities, and then we can say something about the state of the system in future. Okay, we know what is our ultimate goal. We want to calculate vector pi, and we know how to calculate each one of the pi j's. So now let's see if we can find an easier way to calculate pi j for all the possible states of the system, and finally have the whole vector pi. So let's multiply vector pi by one-step transition probability matrix P. So here what I have is the column J of the one-step transition matrix probability P. Okay, so obviously if I multiply vector pi by the matrix P, the result is going to be a vector which is going to have the same size as vector pi. So if the size of the vector pi is 1 by s, and I multiply it by matrix P, which is S by S, so the resulting matrix is going to have a size of 1 by S. Okay, so and for each element of this matrix, for example, for the first element, I have to multiply the vector pi by the first column of this matrix. For the second element, I have to multiply vector pi by the second column of this matrix, and so forth. So if I multiply vector pi by the jth column of this matrix, the value is going to sit here in the jth element of this final vector. So let's see what is the value that is going to sit here. So what is the results if we multiply vector pi by the jth element of matrix P? It's going to be pi 1 multiplied by p1j plus pi 2 multiplied by p2j all the way to pi s multiplied by psj. Okay, so if I want to write the summation of this equation, it's going to be summation pi k multiplied by pkj, where k is going to go from 1 to s. And just note that this summation here that we calculated is actually exactly the summation that we ended up to calculate here. So basically what we calculated here is the same pi j that we calculated in previous slide. So this means that if I multiply vector pi by the jth column of the one-step transition probability matrix P, what I will get, which will be this element of the resulting vector, will be pi j. Okay, so that's exactly what we calculated here based on the calculations in this slide and the previous slide. So the result will be pi j. Similarly, if I multiply vector pi by the first column of the transition probability matrix pi, I will calculate pi 1, pi 2, and all the way to pi s. Okay, so what does that basically tell us finally is that if I multiply vector pi by the one-step transition probability matrix P, what I will get is vector pi. So we always have the one-step transition probability matrix P for any Markov chain. What we need to calculate is vector pi. So if we put this equation together and we solve it for all the values of vector pi, we can calculate the vector of a steady-state transition probabilities for any stochastic system. Now let's see how this whole calculation works in an example. Let's go back to the COLA example. So the one-step transition probability matrix in that example is this matrix, and if you want to calculate vector pi, since there are two possible states in the system, obviously vector pi will have two elements, pi 1 and pi 2. Pi 1 shows the probability that the person is a COLA 1 drinker in the long run in the steady state. Pi 2 shows the probability that the person is a COLA 2 drinker in the equilibrium in the long run. So how do we calculate vector pi? So based on the equations that we just saw, we have to solve the equation of vector pi multiplied by one-step transition probability matrix P equals to pi. So this is going to be, now we have to multiply vector pi by the first column of the matrix to get the first element of the resulting matrix. So that would be, and similarly we have to multiply the vector pi by the second column of matrix P to get the second element of vector pi on the right side. So that's going to be, so here basically we have two unknowns, pi 1 and pi 2, and we need two equations to be able to calculate these two unknowns, right? So however, these two equations that we need should be independent from each other. Now let's see if these two equations that we have are independent from each other. If that's the case, then we are good. If that's not the case, then we have to find a way to come up with two equations of these two unknowns that are independent from each other. From the first equation, I can get 0.1 pi 1 equals to 0.2 pi 2. So if you bring all the elements that have pi 1 into one side and all the elements that have pi 2 into the other side, this is what you get. From the second equation, we also get, so what does that mean? That means basically these two equations are the same. They are not independent, they are dependent, and they are exactly the same. So what does that mean? That means having these two equations together is not going to help us because they are basically the same equation. So we can drop any one of them, either the first equation or the second equation, it doesn't matter. But you can just delete any one of them because they are basically the same equations. So what happens is that I'm going to be left with one equation of these two unknowns, pi 1 and pi 2. So I need one more equations of these two unknowns so that with two equations I can do the calculation and find the values of pi 1 and pi 2. So what is the other equations that potentially can help me with that? So one thing that I want you guys to pay attention to is that the summation of all the steady state properties is 1. So basically pi 1 plus pi 2 equals to 1. So this holds for all the stochastic processes or Markov chains, meaning that the sum of the steady state probabilities in any stochastic process is 1. So this can be written as sigma pi k, where k goes from 1 to s equals to 1. So it's very important to know this equation, and for this system we can write as pi 1 plus pi 2 equals to 1. So what does that mean? That means that in the long run, in the equilibrium, the system is finally in one of these states, either state 1 or state 2. If the system has s possible states, the system finally in the long run is in one of these possible states. So the sum of these probabilities is obviously going to be 1. So now I have two equations. This is my equation 1, this is equation 2, and I have two unknowns, pi 1 and pi 2. And with these two equations, I can find the values of pi 1 and pi 2. So this means that in the long run, the probability that a typical person is going to be a cola 1 drinker is 2/3, or about 67%, and the chance that the person is a cola 2 drinker is a 33% chance. And if you remember, when I raised the one-step transition probability matrix for the cola example to the power of 5, to the power of 10, 20, 30, and so forth, we saw that n-step transition probability matrix started to converge at some point. So we started to observe values like this for P30, and we showed that these values are not going to change as we increase the number of steps. So as we go from 30 steps from now, or 30 purchases to 100 purchases to 200 purchases and so forth. So this is what we call as steady state probability of pi 1 and steady state probability of pi 2, the chance that the person is a cola 2 drinker in the long run. And these are exactly the pi 1 and pi 2 that we calculated here. So as you can see, pi 2 is 2/3, so it's about 67%, and pi1 is 1 over 3 is about 33%. So all these pi1 and pi2 that we could potentially calculate by raising one step transition probability matrix to power of 100, 200, and so forth, those are the ones that we can easily calculate by solving this equation, and that's exactly what we did in this example. So one more thing I want to mention that is that if we go back and look at the COLA example, we had the one-step transition probability matrix, but then we calculated a 3-step, 5-step, a 10-step transition probability matrix, and we saw the change in the transition probability values going from one scenario to another. And then finally we saw that these transition probabilities values started to converge after we got into 20-step transition probability matrix, 30-step transition probability matrix, 100-step transition probability matrix, and so forth. So for these scenarios, when the transition probability matrices have not converged yet, and they're changing as we go from 3-step to 5-step to 8-step to 10-step and so forth, we call that a transient behavior, or we call that the short-run behavior of the stochastic process. But when gradually in the long run, these elements of the transition probability are going to converge, and we can calculate the CityState probabilities. So this is the situation where we call it as CityState behavior or equilibrium behavior. And we are usually interested in finding the behavior of the system in equilibrium or steady state. So if we can calculate that, then we can predict the long-run behavior, the long-term behavior of a system.